Thank you for the invitation to come speak to you today. So what I'm going to talk about today is climate change. And it's something you've probably all heard about in the news or read about. And so I'm just going to talk about some of my research looking at the effects of climate change through the past 550 years and predicting what might happen to our fish populations in Ontario and Canada into the future over the next 50 to 100 years. This is a graph that's called the hockey stick curve that you may have heard from Al Gore, for example. So on the x-axis here, we've got year from 1880 to 2010. And on the y-axis, we've got carbon dioxide concentrations. And on the z-axis, global average temperatures in Fahrenheit. And so if we look at the yellow line first, that's the carbon dioxide concentrations that have been measured at Mauna Loa in Hawaii. And the red line here represents carbon dioxide concentrations as measured from ice cores. So what you can see in the last 130 years is that carbon dioxide concentrations have been going up at a pretty fast rate. And as of March 2014, they're now over the 400 parts per million mark. So they're continuing to rise. Concurrently, if we look at temperature, global air temperatures in this black line, what you can see is that they've also been increasing from 56.5 degrees Fahrenheit up to 58.1 degrees Fahrenheit. So in the last 120 years, we've noticed that carbon dioxide concentrations are increasing, but so are air temperatures. And so what's in store for the future? So the Intergovernmental Panel on Climate Change releases reports every 5 years to talk about the state of the climate. And what you can see here is on the x-axis, we've got year, and on the y-axis, changes in global surface air temperatures. And the black line here represents what we've seen so far in the last 150 years. And then there's some variation. So you can see up to 1 degree change, half a degree change, to over 12 Celsius change. And so what's this variation represent? Well, these are different greenhouse gas emission scenarios. And so the best case scenario is RCP 2.6, which would predict that we just stop emitting greenhouse gas emissions right now. And if we do that, our air temperatures are going to stabilize by about 1 degree Celsius, maybe a 1 degree Celsius increase in the next 300 years. However, if we continue emitting greenhouse gases as we are now, the air temperature predictions are much higher, as you can see, ranging from, on average, over 8 degrees Celsius. So this has huge implications for our ecosystems, but also for our adaptation and our ability to do well and live well on Earth. But air temperatures and precipitation aren't expected to change uniformly across the globe and also across the year. So different seasons are expected to warm and get wetter differently. So in this top panel, we have changes in average air temperatures. And so this figure here represents the best case scenario if we stopped emitting greenhouse gases versus business as usual, where we continue to emit greenhouse gases as we're currently going. And what you can see is that northern regions, so warmer colors represent higher temperature increases, while northern regions are expected to warm faster than anywhere in the globe. And that just so happens to be where we live, up here in Toronto. So we're expecting to warm up faster than other places in the world, and that's going to have huge implications for us. For example, winter tourism, or different sorts of economic pressures, as well as social issues as well. As for precipitation, the situation is a bit different. So blue represents wetter areas, and orange represents drier areas. And what you can see is that it's not consistent across the globe either. And there's a general saying that wet areas are expected to get wetter and dry areas are expected to get drier. So Regions such as, for example, California or Nevada are already pretty dry. They may experience more drought. If they have less water availability and less precipitation, what does that mean for us in Canada, who have quite a large number of lakes, up to 7 million lakes in this country, and people may wanting our water supplies. So that might create some issues for the future as well. But I'm going to focus on the environment, so because I work on, I'm an ecologist, so I work on how environmental stressors impact the environment. So the first thing I'm going to do is go into the past, and that means looking at how lake ice has been changing for the past 550 years, how water temperatures are changing around the world in the past 25 years. And so are we seeing any indications of a changing climate by human observation records? And then from there, I'll go into the future to look at what might happen, what might happen in the next 50 to 100 years for fisheries in Ontario and Canada. So the first story I'm going to tell you about is ice. So the great thing about ice records is that they're collected every year, and what it entails is somebody going out to a lake and observing if the lake has melted, the ice has melted off the lake, or when it freezes. So the date of ice freeze and ice melting. And there are over 100 lakes around the world that have been collecting this data for the past 100 years. And so we can use this information to get an idea of how the climate's changed over the past 100 years. We know from our research that ice records are sensitive indicators of climate and weather. And so lakes tend to melt in the spring when there are warmer temperatures, as well as high wind events. And they also seem to integrate climate as well. So things like El Nino Southern Oscillation, North Atlantic Oscillation. So all these large-scale climate drivers are integrated into the ice records. And the question that I'm interested in asking right now is, how has climate changed in the past 550 years? And I can do this using the longest lake ice record ever collected, as well as 75 other lakes. But this lake is particularly interesting. It's Lake Suwa, found in the Japanese Alps. And monks have been recording the date the lake froze since 1442. So for 550 years, Shinto priests have been going out to the lake to see when did the lake freeze. And they've kept these records for scientists to use now, which is fantastic. And that's because there's a legend and folklore associated with this lake. And so the story goes that at this lake, Lake Suwa, there's a monastery and a shrine on one side of the lake. And in this shrine, a god and goddess lived together. And as sometimes happens when people live together for too long, they get into a disagreement. And so the goddess moved out, and she made herself a shrine on the other side of the lake. And so they'd been separated, but every year when the lake froze, they saw these ridges in the ice. And so, but they had a really good explanation for it. So every year when the lake froze, the god would go across the lake and visit the goddess at her shrine on the other side to make amends and ask for forgiveness. And he would leave his footprints and the tail of his dragon behind. So he walked across the lake with his dragon, and the ridges look like the tail of his serpentine dragon crossing the lake with him. And so this happened every year, and they documented this, and it was a celebrated event. And so Shinto priests would go out to the lake and have a ceremony to celebrate this event, because it was believed that when they found these ridges, it was a lucky sign, and that would mean a bountiful harvest and a good year. And so they had a celebration. And they've done this every year since 1442, which is pretty fabulous that these monks had the insight to do this and record it for people to use. So my collaborator, John Magnuson from the University of Wisconsin-Madison, went to Japan, and he went to visit the shrines, and he talked to the priests and the limnologists. So a limnologist is somebody who studies lakes, and so this is a limnologist at the lake, and they went through all the records of when the priests and the monks had written down when the ice, the lake froze. And so from there, we can start asking scientific questions on that data. And so first, we just mapped out what was the ice record like for the last 550 years. And so what you can see here is year. So it's a really long record, and it's collected by humans every year, from 1443 to here we have up to 2003, but there's more data. And then the day of ice formation. So 0 is January 1st, and the days that are negative are days before January 1st, and the days afterwards. So you can see between, say, 1443 and 1703, the lake froze generally before January 1st. So generally it was freezing at the end of November. Between the mid 1700s to the mid 1800s, we start seeing the lake freezing later. These points here are also represent the years when the lake didn't freeze at all. And so we're now starting to get an indication that the lake isn't freezing in some years. Since the 1880s, you can see that on average, the lake is freezing after January 1st. And so within this time period, the lake has shifted by over 30 days in the timing in that it freezes. And coincidentally, this shift, this break point, happened in the mid-1800s. And I've analyzed data like this for about 50 other lakes, and they all happen around the mid-1850s. So what happened then? Well, it happened to be the end of the Little Ice Age, the start of the Industrial Revolution, and in Japan and in many other regions, there was a lot of land use change. So at the same time that all these major events were happening, we see like an increased rate of change in this Japanese lake, but lakes across the Northern Hemisphere. And so I mentioned something about the lake not freezing. So what you can see here again is time, the time period binned into 50-year periods. And on the y-axis, we've got probability of no ice. So what you can see from 1443 to 1700, the lake did not freeze 3 times, only 3 times. In the last 50 years, the lake doesn't freeze 1 out of 4 years. And so within just looking at simply, does the lake freeze or not, we've seen this dramatic change in the ability of this lake to freeze because it's just too warm. And so this is not good for the folklore as well, which suggests that it's bad luck when the lake doesn't freeze and a poor harvest is about to be yielded. So, so things have changed quite dramatically in the last 550 years. So what we wanted to do, this is kind of a crazy graph and a crazy analysis, was look at, so we know that the ice is changing over the past 550 years, but are these climate drivers also changing? And you may have heard of El Nino, Southern Oscillation Indices, and they've always been 3 to 7 years. You've heard of probably the North Atlantic Oscillation that also follows a cyclical pattern. There's also the sunspot cycle that happens every 11 years. But we're interested in knowing, are these climate drivers staying the same or are they breaking apart as well? And so this is a sophisticated analysis, a wavelet analysis, but I'll just show you what the main points are. So here we've got time, again, on the x-axis. And then on the y-axis, we've got period in years. So these are the cycles, the different cycles that we have evidence for. And so we're looking at these red regions. And so Here's a line that is after the start of the Industrial Revolution. And what you can see is in the past, we had significant cycles between 1610 and 40 years, 64 years. We've got the 5 to 6 years. We've got a bunch of different cycles that are appearing as significant. So those all represent like the El Nino oscillation, this North Atlantic oscillation, sunspot cycles. Well, look what happened here after the start of the Industrial Revolution. They're not showing up in the same way. So there seems to be evidence in the ice record, but also in different types of studies that these large-scale climate drivers are breaking in their cycles. So things that we've known to be constant over thousands of years no longer seem to be a constant, which is a bit of a worry because of the implications that it might have. And as I mentioned, the situation is not specific to this lake in Japan. And so here, these are 75 lakes and their melting rates in the last 100 years. And so I've broken it down by different regions. And then the number of days that the ice melts earlier, just in the last century. So on average, lakes around the Northern Hemisphere are melting 7 days earlier, a week earlier. But there's variation from one of the lakes in Asia, in Russia, did not change at all. Whereas some lakes in North America are warming 24 days earlier. So that means 3.5 weeks less winter on lakes in the last 100 years. So let's compare what's happening in the last 50 years to this. So here we've got in blue the 50-year period and in pink the 100-year period. And again, these different regions, as well as the average rate of change in ice breakup date. And what you can see is across the Northern Hemisphere, lakes are warming 4 times faster in the last 50 years than they were in the past 100 years. So there's something going on in the environment that's translating to lake ice. And so I'm an ecologist, but I'm a quantitative ecologist, so I do a lot of statistical analysis and computer modeling. And using those tools, we can address why might be seeing these patterns. And there are 3 major factors to explain that. So lake ice is melting earlier and freezing later because of climate change. There's a clear signal between increases in air temperature as well as increases in greenhouse gases, such as carbon dioxide, with earlier melting dates and later freezing dates around the Northern Hemisphere. We've got things such as these large-scale climate drivers, so the El Nino Southern Oscillation and the North Atlantic Oscillation, as well as sunspot drivers. So those are contributing to ice-off as well. And then local weather, such as temperature, precipitation, and snow cover. And so I used this model to, when I was a postdoctoral fellow at the University of Wisconsin-Madison, we had this ice pool, and it was a bet to see who could predict when the lake ice would melt every year. And so I developed this statistical model, and we could use whatever we wanted to see if our models worked well. And I won the ice pool, and I was like, okay, I guess this is a good model if I can predict what's happening in a particular year. So we've gone to the far past, and now I'm interested in what's happening in the recent past. And we can do this through a collaboration that I'm involved in, and it's the Global Lake Temperature Collaboration. And this involves over 80 scientists from around the world. And we've come together to look at how to collect water temperature information for the last 25 years all around the world. So we have data from all of the different continents. And then we've teamed up with NASA to see if we can detect climate change from space as well. So we've got records from on the ground, well, in the lake, and then we've got records from space to see if water temperatures have changed over the past 25 years. And so this is our data set, and you can see that, so in yellow are the lakes, So yellow are the lakes that have been collected in situ, so that means people going to the lake every year it's every 2 weeks to check what the water temperatures are. And then in red, we have lakes that we can detect from space. So these lakes are larger lakes. They have to be about 1,000 square kilometers for the space scientists to be able to see what the water temperatures are. And again, what we have is in red, these are lakes that are warming, and in blue, lakes that are cooling. And you can see a lot of red dots around the globe. And so 90% of the lakes we're finding are warming around the globe. And the largest amount of warming seems to be in the northern regions. So Canada, Northern Europe, those all seem to be warming pretty fast. There are also some lakes that are cooling. So you might see some in the Alps, and then lakes in Florida are cooling. And then it turns out, well, these lakes are cooling for all the same reasons. And it so happens that there's more inputs going into the lake because of land use change. And it's decreasing water clarity in the lakes. So those lakes are actually cooling, although the climate around them is warming. But the interesting thing is that historically, we've just looked at what happens in the lakes around us. And we assume that the water temperatures and the way lakes behave is just because we're all in the same region. But here we've taken a global perspective, and we can see that lakes around the world are behaving similarly if they have the same characteristics, which is pretty cool, because then it can give us an idea of how to manage these types of lakes. And I'm not going to go into all the modeling that was involved, but we wanted to know, why are these lakes temperatures changing? And why are they changing so much in the past 25 years? Well, there seem to be two major factors that are contributing to this. So the first is climate change, which we've seen lots of evidence for. And as air temperatures are increasing, water temperatures are increasing. The second is one of the first times that we've have evidence of this global phenomena going on. And this is called solar brightening and dimming. And so what solar brightening and dimming is that in the Northern Hemisphere, so for example in North America, in the past 25 years, we have less cloud cover. And we're doing a little bit of a better job of not having so many coal-fired plants, releasing particulate matter. And so it's just a bit brighter than it was before. Whereas regions in the Southern Hemisphere, especially around Asia, those areas are getting dimmer. And that's because of all the particulate matter being released into the atmosphere. And so these two factors are combining with one another to influence what happens to water temperatures in a lake. So regions that have increased air temperatures, but also solar brightening, and there's more solar radiation hitting the lake, those are warming much faster. And so those are lakes around here, which you'll see has big implications for our fisheries. And so this adds like an extra layer of complexity of how do we deal with this problem, because we have to deal with this air temperature problem and climate change problem, but it seems like we have to deal with this solar brightening and dimming problem as well. So now what I'm going to do is go into the future. So we've talked about the past, and it seems like lakes are changing. There's a lot of evidence that lake ice dynamics are changing, their water temperatures are changing. So what does that mean for the things that live in the lake, like fish? And so this first study that I'm going to talk about is a bit of what I did during my PhD. And so the question that I was interested in asking was, will smallmouth bass expand their range under climate change scenarios? And smallmouth bass is a warmwater fish, and it's a sport water fish, but in Ontario, it's a non-native species. So it's not supposed to be here. But people really like fishing for it, so they bring it here, and I'll show you how they go about bringing it here. And so many studies, so physiological studies and laboratory studies, have suggested that the growth rate of smallmouth bass is related to air temperatures. So if we've got air temperatures on the x-axis and the length of the fish on the y-axis, if air temperatures are below 18 Celsius in July, the fish doesn't get big enough to survive the winter. If the air temperatures are above 18 Celsius, the fish gets to be a big enough size to survive the harsh winters. And so how are bass moved? And so, as I mentioned, they're historically haven't been here, but as of the 1850s, people started moving them. And this included the government as well as anglers. And so what government, Ministry of Natural Resources type people, scientists used to do was they'd ride the railroads, and as they passed a lake, they would throw smallmouth bass into the lake. And that was how they stocked so many of these lakes in Ontario. Another approach to use was to fly by with an airplane. And so you fly over a lake, over a lake in your airplane, and you just dump the fish out as you go into the lake. And so that was some ways that these bass were moved around. Other ways they're moved around, so they're now found in BC, it's because fishermen love to fish for them. So they bring their bass from wherever they may be and dump them into the lake that they want to go fish in, because it's apparently fun to fish for them. And then we've got natural networks. And so fish can just travel, as you know, through rivers and lakes. And so they just make their way, but much more slowly through the lake-river network. But what's the problem? So they may be fun to fish for, but do they have any impacts on the ecosystem? Well, many studies have shown that when bass are in a lake, so here's a cartoon where there's bass in a lake and no bass, there's very little of these minnow species. So they're pretty great predators, and they consume a lot of small minnows. And the diversity of minnows is reduced when bass have invaded a lake. But there's other consequences as well. So one species that you may be familiar with is lake trout. And lake trout is a top predator. And in Canada, it has really high socioeconomic importance. So in the north, much of the income through fisheries is related to tourism, bringing in Americans to come to Canada and fish for these lake trout, because in the US, there's very few lake trout left. Within the continental US, there may be only 3 to 4 populations left. So there's not that many lake trout left in the US, so they come to Canada to fish for them. And so it has ecological importance, but also socioeconomic importance. And what you can see is that, so lake trout live in deeper portions of the lake. So this is called the pelagic zone. And smallmouth bass live along the near shore. And it's called the littoral zone. And so typically, smallmouth bass and lake trout don't interact. So smallmouth bass eat whatever they're eating up here, and lake trout do their business deeper, more offshore areas. However, particularly in Canadian lakes, lake trout sometimes come up to the nearshore area to feed. And when there are no bass within the lake, stable isotope analysis has showed that 60% of the lake trout's diet is composed of these small minnows, and 40% of these tiny zooplankton, especially if they don't have their forage fish in the deeper portion of the lake. So they come up to the shore, near shore area and eat these smaller fish. What happens when bass are in the lake? Well, as I mentioned earlier, they've eaten all these small fish, And so now the lake trout's diet is 20% of these small fish and 80% of these plankton. And so what this leads to is reduced growth, survival, and fecundity, so reproductive ability of lake trout populations. So those lake trout populations are vulnerable. However, if there is a nice forage fish community available in offshore regions, more deeper offshore regions, then the lake trout's fine. So then the lake trout and the bass can coexist in a lake without too many repercussions. So what I did for my PhD was, so during my master's I worked on Lake Erie, and when you go through the peer review process, people sometimes say, well, you only worked on one lake, so can you really say anything about the ecosystem and how things might affect an ecosystem? So I started my PhD and I was like, oh man, I need to get more lakes. And so I got 50,000 lakes and in hopes that it would be enough. And it turns out it is enough. So I had information on where the lake was, how big the lake is, how clear it is, what kind of nutrients do they have, and then what fish live in those lakes. And from there, I could answer a bunch of questions. So first, I wanted to know, where is the habitat for smallmouth bass right now in Canada? And so again, there's lots of statistical models involved, but then you get a pretty picture. So the red regions represent suitable habitat, and the blue is unsuitable, and yellow is potential habitat where they may be able to survive. And what you can see is that the bass tended to live in more southern regions of Canada, and this sort of fits their distributions. And so what I did was I used some climate change scenarios from the time to predict what might happen 100 years from now. And here is what the picture looks like. So bass could theoretically be found throughout Canada. And there's suitable habitat for this fish because water temperatures have increased so much, are predicted to increase so much, that these bass can then survive the winters within these lakes. And you wonder, how might they get here? Well, we talked about people moving this fish, but there's also this continental divide right here. And when I was doing my PhD, the bass hadn't crossed that continental divide. And so I thought, okay, that's fine. But while I was doing my postdoc, it took like 2 years, they crossed the continental divide. And what that suggests, what that means, is that these bass can now naturally move because all the rivers flow north, following the continental divide. So they can naturally just move up to these northern systems. And so I was curious to know what was happening in the southern extent of the range. Were the bass just shifting northward? Were they just moving up? Or were they also being found throughout the US and the continental US? And it turns out they are. So the red region represents, again, suitable areas for bass to live in and where they're predicted to occur. And you can see that with this model, the northern region is similar to the previous habitat model, where they're limited by summer air temperatures. So if summer air temperatures get warm enough, then these young of the year bass can survive the winter. We also have an expansion in the south, and that's because they're limited by winter air temperatures down there. And the winter air temperatures in the south are not expected to change all that much. And so bass have the potential to be found throughout North America. Well, what does that mean for fisheries? So coming back to Canada, I then looked at how many populations of lake trout might be vulnerable in our lakes. And I divided them up into 3 categories. So smaller lakes, medium lakes, and larger lakes. So smaller lakes tend to have simpler fish communities, so they might not have access to those additional forage prey. And then lake trout are expected to have less habitat because they need cold water habitat that's well oxygenated. And within smaller lakes, there usually isn't a refuge, especially under climate change scenarios, for a well-oxygenated, colder region within the lake, as opposed to larger lakes. And what you can see is that I predicted, it's a really broad prediction, 10 to 20,000 lake trout populations could be threatened by as soon as the year 2100 within Canadian lakes. And lake trout found in smaller lakes are particularly vulnerable to the invasion of bass. So from this study, I was contacted by the British Columbia Ministry of Environment and the Department of Fisheries and Oceans Canada, because bass are now being introduced into British Columbia lakes. And as you know, British Columbia is famous for its salmon fishery and trout fishery. And if this invader comes in, what impact might that have on their fishery? And so we developed some models to look at how might bass invasion influence the fish diversity in these British Columbia lakes. And so first we need to figure out, so when you're looking at invasive species, first you need to identify, can they even get there? So, so this information was based on like how many people are there, what kind of lakes, what boating pressure is there, and are they even able to access these lakes? So of the 67,000 lakes in British Columbia, there are about 727 that have the potential for people to bring bass in. So once a bass gets into a lake, it has to survive and have a reproducing population. And so you then have to identify, is this habitat suitable for the invaders to establish? And so of these 727 lakes, we identified 138 of those lakes have currently suitable conditions for bass to survive. This may change into the future, but we're interested in what's happening right now. And so what are the impacts on these native biota? And we're just focused on these, sorry, this is a bit violent, the bass killing the trout. But what are the vulnerable lakes? And so what we found was that 88% of the trout in those lakes would be vulnerable to extinction, 14% of salmon populations, and then 21% of minnows. So that's a pretty dire situation for a trout and salmon fishery, as well as biodiversity within these lakes. And so now the Department of Fisheries and Oceans is monitoring these lakes to keep bass out because those particular lakes are highly vulnerable right now. And so since I've been at York, a couple of my graduate students are looking at how climate change is going to affect warm water, cool water, and cold water fishes in Ontario. And then the idea is to then understand what this might mean for walleye populations and lake trout populations and how they might interact in the future. These are important species ecologically, but also commercially. And then what does that mean for ecosystem resilience? So will our Ontario lakes be able to be resilient to the effects of climate change into the future? And so the interesting thing is, since I finished my PhD and started working at York, the climate change scenarios have changed quite a lot. And what used to be considered extreme 5 years ago is now considered to be a middle of the scenario run. So our models now are even more extreme than they were that I predicted 5 years ago. So it's kind of amazing how much things are already changing. And so here what we have is smallmouth bass. So there's a lot more records of smallmouth bass than there were 7 years ago. And so bass are moving up into more north central regions of Ontario where they didn't exist even 4 years ago. And so here is where we're expecting bass to be if we stopped emitting greenhouse gas emission scenario today. And what you can see is that they'd be in the south central region as well along the western shores of Lake Superior. So that's not so bad for biodiversity, considering that they're already there. What would happen in a similar time period if we continue to emit greenhouse gases as we are doing now? What you can see is basically, if it's red, there's a high likelihood that the bass will be there. If it's blue, there's a low likelihood that they'll be there. And what you can see is that using 126 different climate change scenarios, most of them predict that bass will be throughout Ontario. And that's not a good situation coming up by 2050 and 2070. And so what are these other predator and forage fish going to be like? So if we look at the walleye situation, walleye is a cool water fish, but it's a very important commercial fish. And it's distributed across Ontario. And by 2070, we're expecting walleye, so this blue range is where walleye are expected to disappear from. So there are going to be no walleye within southern and south central Ontario. And this is not just using one climate change scenario, so now we use all of the climate change scenarios. So it's an amalgamation of 126 different scenarios of climate change. Where they're found in the highest abundances right now in central Ontario, their likelihood of occurrence is about 0.3 to 0.4. So there's a large probability that these walleye are going to be gone from where they're currently found in pretty high abundances. So where are they going? They're just moving north. And so they're just shifting their range northward. And this is the first time that we've been able to, cool water fishes are a little tricky because you don't know if they're going to do better under climate change or worse. But with these new climate change projections, it seems like they're going to be in a tougher situation than we would have predicted even 5 years ago. And what about the cold water fishes? So here we've looked at Cisco, but lake trout have similar sort of occurrences. And you can see that Cisco are found throughout central and northern Ontario. Cisco are an important forage fish that are important for lake trout and keep bigger fish happy. And what you can see is that in central and southern Ontario, they're all blue, which suggests that they're going to be gone. So by 2050, so that's within 35 years, we're not going to have these cold water fish that were historically present everywhere in Ontario. And where are they all going? They're all being squeezed into these corners in Ontario, close to the Hudson Bay. And so that suggests that the cold water fishery may collapse within the next 35 years, which is not a good situation for our fisheries, but also our ecosystems, because how will our ecosystems adapt? Well, we may just have more warm water fishes, but what does that mean for all these cold water fishes that were sort of part of the Canadian identity? But I don't want to depress you, because I've sort of tried to indicate that we can do something with these models. So if we start curbing greenhouse gas emissions, the scenarios are not that bad. We may lose some fish, but not to the extent if we keep going at the rate we're going. The other thing that everyone can do is not move fish into different lakes. So if you're fishing and you get some bait, it's a good idea not to dump your bait into the lake that you're fishing in, because you're transporting invasive species. An invader is goldfish, and goldfish have primarily been spread around by humans. So if your tank gets too big, or I don't know, you don't want your kids to know that your fish is not doing so well, you might release it into your local stream and lakes, and then these fish move around. So that's how a lot of invasives actually get around. So there's things that people can do to help mitigate the situation, which will have a beneficial effect for our ecosystems. So just to wrap up, I talked a bit about the past and a bit about the future. So what I hopefully showed you is that lakes have been changing over the last 550 years, and we believe this is in response to climate change. And so for the future, if we continue to go on our current trajectories, this could lead to a lot of our loss of our native fish populations in the next 50 to 100 years. So thank you for your attention.